Hello, my name is Amanda Gracel Olson, and I'm going to talk about tangent lines, secant lines, and how to use limits to find derivatives, and then also how to find the equation of a tangent line using limits and derivatives. This video isn't going to have a lot of proofs or any kind of rigor. We're just going to talk about it and present some theorems without proof. So if you're wanting that rigor and that formal proof, this is just going to be that campfire talk, and you're going to want to look for a different video. We'll have a little bit of examples, but I'm not going to go in depth into how to do some of our problems from this unit. This video will be especially helpful if you're in my calculus class at MCC. And yeah, so let's go ahead and look at what we've got here. So first of all, I want to talk about what is a secant line. So if you have a graph that is a curve, like this, then a secant line is a line that crosses, there are 2 points on the curve, and it's a line that is connected through those 2 points. Okay, and you can get infinitely many secant lines for any curve, right? Because you're only just picking 2 points. There's infinitely many ways to do that. Ideally, though, we find a series of secant lines, and we start choosing values of x. So we have our initial x, and then an x value to the right. And with those, the x values that we choose, if we choose x values that are closer together, then we get a better, we have a secant line whose slope kind of resembles more of the change of the curve. Okay, so you can kind of see that starting off, if we're far away, our secant line, you can see that doesn't really resemble the curve. There's some variation. Less variation as I pick 2 x values that are really close or closer together, and even closer than at some point, it kind of looks like you can't even tell that there's 2 points in a line going through it. It almost looks like it's just directly the curve, to the point where we have the same 2 points, 2 x values, then we look at the secant line. Now, the way that you find the slope for a secant line or any line is you take the difference in y values with respect to the difference in corresponding x values. So you have that ratio of y change to x change. When you're dealing with x values that are really close together, what's happening is your difference of x values, when you take with a loss of generality, the larger minus the smaller x value, you take the difference of those two, you're getting something that's getting smaller and smaller. It's getting closer to 0. However, we can't have 0 in the denominator. We know, you divide by 0, that's undefined. So we get kind of stuck when we try to find the slope of the tangent line or a secant line where we're working with 2 of the same points. Okay, so let me graphically kind of show you. So here, this is using Desmos, and I've graphed the function f of x equals x squared plus 1. And then this a value is my first initial x, and h is just the distance away between my first and my second x value. So if I have x equals 1, or a equals 1, so if I have, a, which equals my x1, my x2 is going to be equal to whatever x1 was plus that h. So in this case, this specific example, we have it equal to 1. So we have 1 plus, however far apart I choose for my next h value. So that could be, let's just say 0.5. Okay, the next 2 is 1.5. So you've got two values. H is the difference or distance between those two. A is your starting X value, and then H tells you how far it is to the previous X value. So then you'll have 2 points you can see, and you make a secant line through those 2 points. Okay, so I've kept this first one, like I said, consistent. X is 1, Y is 2, and then this other point, I'm kind of increasing or decreasing my H value to kind of see how it compares. And then this automatically creates the graph of the secant line. But you can see what really seems to lie tangent to the curve and look like it's tangent to the curve is right when you have your H being 0. If you look at my H values, the larger they are, of course, the less our secant line resembles the curve. The closer it gets, the more it resembles that tangent line to the curve. And we can't talk about, again, though, that H being 0, because if H is 0, that's the difference of our X values, and that is also results in the slope of your tangent line. The slope of your line will have a denominator of 0, and we can't divide by 0, that's undefined. Another way that you can see this is here you have this f of a plus h, and remember that's your initial X value. So if you wanted to, you could call it f of x minus f of x plus h minus f of x. In other words, this is kind of your y2, this is your y1, and then h just comes from taking that x2 and subtracting x1. Remember, h is the difference between those two values. And we get the slope of this tangent line, or we get the slope of the secant line by using the standard slope formula for these 2 points. But like I said, we really want to look at the two X values being the same, so we can get that tangent line and we can talk about, well, what's the slope of the tangent line? Well, in calculus, if we can't actually evaluate something, if we're working with a function where a point is undefined, in this case, we can't have that H be 0, but we want to know what happens if H was 0. In calculus, what we do is we use limits. So, okay, we can't look at H being exactly 0, but we can talk about what happens as H gets smaller and smaller. What's happening to my slope, or that difference quotient, it's sometimes called that ratio of Y with respect to the ratio of X, that change in Y over change in X. What's happening as our X values get closer and closer together? In other words, what's happening to that change in Y over change in X as H gets smaller and smaller? And we have a term for that. Nope, pushed the wrong button. Sorry about that. And so we say that we talk about the limit as delta X approaches 0. Now, if you meet with me in person, I'll say, I don't like to use delta X. I like to use the symbol H. It's just a different letter. So you could put in a delta X, just means that difference in X values, but you're really looking at what happens as that difference in X values gets smaller and smaller. Okay. And when you find that limit is actually evaluated to be m, or the slope of the tangent line, or the instantaneous rate of change. What this can help with is a variety of different topics. It can help you to find, first of all, the slope of a tangent line. It can help you to find a tangent line. Tangent lines can be used a lot in various topics, one of them being, if I have a position function, and this is my position function with respect to time. So for instance, if I was going to drive from Omaha, Nebraska, where I'm placed right now, and I'm going to drive to Sioux Falls, South Dakota, I'm going to not go in a straight line. I don't think I'm directed that way. And I'm not going to go at a constant speed. I'll walk from the building I am, I'll get in a car, and in that car, I'm going to alternate speeds as I go. If you are looking at it from kind of an algebra standpoint of like speed that I was going, you would take, starting now, how long does it take for me to get from here to wherever I stop in Sioux Falls, South Dakota, measure that time. And then you'd say, okay, she went this distance straight and then over this much time. We don't look at it that way though in real life, right? We consider that we like to know what's your speed when you're on the highway. Because obviously the speed that I'm running out to my car is not going to be the same speed that I'm traveling when I'm on in the highway. When you get to Sioux Falls, there's, the speed limit increases versus in Sioux City, you get hit with those speed traps. So you have to slow down. So you're not driving at a consistent speed. And so average speed isn't really helpful. We'd like to look at more, what's our instantaneous? So what's our speed right now? My speed right now is 0. What's my speed as I'm walking out to my car? What's my speed as I'm driving on the interstate? Looking at those different speeds can be helpful. And that gives us this idea of velocity. And so that's going to be that instantaneous rate of change. Or if I had a position function, it would be the slope of my tangent line. We're going to see that. We're also going to see tangent lines can be helpful with min and max problems. Okay, because if I look at a tangent line, if it has a horizontal axis, we're going to see that actually alerts us to where there's a hill or a valley. And that hill and valley can tell us about relative min and max. There's some ideas of area problems as well. These are kind of some of the foundations of when limit calculus came about. Area problem is a little bit more something you explore towards the end of Calculus 1 or in a Calculus 2 course, but we'll see that as well. So hopefully this gives you at least a starting point of what the derivative is, what the tangent line is. And so the derivative is just the function where you look at the limit as x approaches 0 for that difference quotient. In other words, it's the slope of that tangent line, okay? And it can tell you your instantaneous velocity at any point on a graph. So we had just worked with the function f of x equals x squared plus 1. And we saw that at any point, you can have a different instantaneous rate of change or a different slope for the tangent line. But what is it? That's what the derivative tells us. And we'll have to see in another video how to find that derivative. But hopefully that gives you an introduction of secant lines and tangent lines and where we use them.